All right, guys, so here in Unit 2, we're going to talk a bunch more about some specific ways that we can make an inference. Remember, an inference is something that we are just concluding about a population based on a sample statistic. So these first few things we see here are just vocabulary that we talked about before. A point estimate is something that we use to estimate something about the population. So like we can use a sample mean to estimate the population mean. We can use a sample parameter or sample proportion to estimate a population proportion, things like that. In this unit, everything that we're going to deal with is going to be related to normally distributed sampling distributions. We are going to talk about different shapes as well, but normal is the most common. It's the one we're going to see the most, and it's the only one we're actually going to look at in this unit. So if I'm going to do tests based on the fact that something is normally shaped, then we have to be able to back up the fact that it is truly normally shaped, because it could be other things as well. And so that's why we have the central limit theorem, which we learned about in the last unit. The central limit theorem gives us two additional ways that we can say that a sampling distribution is normal, okay? The old school way from last semester, which we are going to have to go back to at some point, is that we actually plot the data and look at the shape of the data and plot a normal quantile plot and look and see if it's linear. And if all of that checks out, then we can say it looks like it's normal. Okay, this is the kind of like the faster, easier way. We can say if the samples are at least 30 or bigger, fairly large, then we can say the sampling distribution is normal. Or if we have information that tells us the population itself was normally distributed, then the sampling distribution is going to be normal as well. Okay, and after we've decided that that's normal, we're going to look again a lot at the sampling distribution of the sample mean, X bar. We looked at that in the last unit a whole bunch. And it's going to have a mean equal to the population mean, just like before, and the standard deviation equal to sigma over the square root of the sample size, sigma being the population standard deviation. Okay, so there's some numbers we need to know. All right, once we have confirmed that our data is normally shaped, we can use the empirical rule, which we learned about last semester. It says 68% of the data is within one standard deviation of the mean, 95% of the data is within 2 standard deviations of the mean, and 99.7, almost everything, is within 3 standard deviations of the mean. So we're going to use this empirical rule to start to talk about our point estimates. So like our sample, here we have a sample mean. We can use this to estimate the population mean. Like I say, the population mean is around 13.54. So now we're going to bring that a step further and we say, okay, how sure are you that the population mean is 13.54? Can you put a number to that? Are you 90% sure, 95% sure, 94% sure? How positive are you that the sample mean is anywhere near 13.54? So that's what we call a confidence interval. So here we have just a small example that we don't have to do too much work in. We have a normally distributed sampling distribution where X bar, our sample mean, is 13.54, and the standard deviation of our sampling distribution is 0.3, not sigma. It's the actual sample standard deviation, so we don't have to do any math with that. And they have concluded this, that about 95% of the data lies between 12.94 and 14.14. Okay, there's some different things within that statement right there. 95% is the confidence level. Confidence level. So it's the actual percentage that describes how confident you are about your interval. And then this range of numbers here from 12.94 to 14.14, which we actually write like this as an interval in this interval notation. I've seen that before. That is the actual confidence interval. Confidence interval. So that's the 95% confidence interval, actually, in this case. Okay. And so how did they even get those numbers? Let's talk about that for a second before we look at the next part of this. Well, in our empirical rule, it says that 95% of the observations lie within 2 standard deviations of the mean. So 95% of the observations in this distribution are within 2 standard deviations of this mean. So if I take my mean, 13.54, and subtract 2 standard deviations, and then take my mean and add 2 standard deviations, we'll get the boundaries of that 95% confidence interval, which gives us 12.94 and 14.14. Okay, so this is just the number of standard deviations that we need to add and subtract from our point estimate. Okay, let's do the same thing then for a 99.7 confidence interval. According to the empirical rule, 99.7% of the observations lie within 3 standard deviations of the mean. So to get this, all I gotta do is take my point estimate, my sample mean, and add and subtract 3 standard deviations. When I subtract 3 standard deviations, we get 12.64. When I add 3 standard deviations, we get 14.44. So as you can see, that interval is wider than the interval we had before. So it includes more numbers, which is why we can be more confident. It includes more points. So obviously we're 99.7% confident, we're saying that the true population mean is somewhere within that interval. Well, yeah, because that's 99.7% of the data. So of course we're confident that it's in there somewhere. It includes almost everything that there is. Okay, moving on though, confidence intervals in general are always constructed using this form. We say it is always the estimate, point estimate, and that can be an estimate of the mean, an estimate of a proportion, whatever. But we always add and subtract a margin of error. And as you saw in that last example, the margin of error is a number of standard deviations. And that the number of standard deviations we choose is going to depend on how confident I want to be. So in the first one, we added and subtracted 2 standard deviations because we wanted to be 95% confident. In this one, I added and subtracted 3 standard deviations because we wanted to be 99.7% confident. Okay, so what if I want to be 90% confident? In that case, we're actually going to add and subtract 1.645 standard deviations. Okay, that is called the critical z-value. The critical z-value refers to the number of standard deviations we need to add and subtract to our estimate in order to get our confidence interval. And we denote it here with a z because if you remember our standard normal table, when we standardize a value in a normal distribution, it becomes a z-value. And a z-value represents how many standard deviations a value is from the mean. And the reason why that works is because in the standard normal curve, the mean is 0 and 1 standard deviation is just equal to 1. So z star, our critical z value, gives us the exact number of standard deviations we want to be away from the mean. Okay. Going back to 95, we said just a minute ago that 2 standard deviations away from the mean contains 95% of the data. Turns out that's actually a rounded number. About 95% of the data is about 2 standard deviations from the mean. The real number, if I don't round, is 1.96. That's about 2. Okay, we're going to stop rounding it from now on though. Instead of using 2 standard deviations of the mean, we're going to use a bit more of a more accurate number. We're going to use 1.96 standard deviations away from the mean. Okay, and the last one, 99% confidence level, we're going to use as critical z value of 2.576, so a little less than 3. Okay, so there's our numbers here. And we'll talk about on the next page here specifically how you can get those Z stars if you don't have them memorized. Okay, it's actually very quick and easy. There's several ways to get these critical Z values without having them memorized. Okay, but for now, we'll just use that table. So as we said before, confidence intervals will always be your estimate plus or minus your margin of error. Now, when we're looking at sample means in a sampling distribution, we can be a little more specific. Our estimate, if we're estimating a population mean, we're going to use the mean of a sampling of a, the sample mean of a sampling distribution. And then our margin of error will be however many standard deviations we need to go, Z star, times the standard deviation of the sampling distribution, which is sigma over root n, sigma being the population standard deviation and n being the sample size. So we're going to use this a whole bunch this unit. Okay, that is how we calculate the confidence interval for the mean. So let's go ahead and do this now. We have a sampling distribution of a toad jumping length with n equals 250 toads, x bar is 9.2 centimeters, and sigma, the population standard deviation, is 4.8 centimeters. So our 90% confidence interval, we're going to use what we just wrote up here. Plug in what we know. X bar is 9.2 plus or minus Z star. Since we're using a 90% confidence interval, I'm going to use 1.645. Sigma is right here, 4.8 divided by the square root of n, which is 250 toads. Okay, and this is plus and minus, so I'm going to subtract to get the lower end of my interval, add to get the upper end of my interval. So let's just see what that margin of error is first of all. So 1.645 times 4.8 over the square root of 250 on my calculator is 0.499. So my margin of error here is 0.499, or about 0.5. And then when I subtract to get my lower bound of my confidence interval, add, I get the upper bound of my confidence interval. So what we can conclude here is that we are 90% confident that the true mean of the population is within this interval. Okay, so let's go back to those critical Z values. Up ahead here, I said that the critical Z value for a 90% confidence level was 1.645, and I didn't tell you how we got that number. So memorizing it, of course, is going to be helpful, and we're going to use it a lot. So you might end up having it memorized by the time we get through this unit. But if you don't have it memorized, that's fine. There's a lot of ways we can find these. If my thing will, there we go. So if we're looking for a 90% confidence interval, this is what we're looking for. We are looking for the values here and here, which contain 90% of the data. So Z star refers to what these values are here and here at the boundaries in the standard normal curve. Because in the standard normal curve, one standard deviation is 1. So to figure this out, we can do a couple of different things. We can use our standard normal table, or we can use a calculator. Let me show you how to do it using a standard normal table first. Remember, you cannot use a graphing calculator on all portions of your AP exam. So you need to know how to do these things without a calculator when you have to. And you will have to at least once. So if I'm going to use my standard normal table, I first need to decide what area we're looking for. The area between these two curves is 90%, or 0.9. But in our table, it only gives us the area below a certain Z value. So if I plugged in this Z value here into my table, it would give me the area below it. Not between, not above, it's always below. So let's think about what we have here. This is 90% of the data, which means these other two tails here have to contain the rest. So what's left, if 90% is yellow here, then the rest has to be 10%, right? 90 plus 10% is 100%. And these two tails are identical, right? It's a symmetrical shape here. So if they're each the same and they have to be 10%, that means each of these tails has about 5%. 5%. Okay, so all together I have 0.5 here, 0.9 here, and 0.5 there. Add them up, you should get 1. 0.5 plus 0.9 plus 0.5 is 1. So when I look at my table, this negative Z star here will have 0.5 of the data below it. And this positive Z star over here will have 0.95 of the data below it. So I can look for either one here. They should be the same number, one positive, one negative. So let's look for both. Let's see what Z star corresponds to 0.5 and what Z star corresponds to 0.95. They should just be opposites. So starting with 0.5. So again, the areas or the proportions or percentages are inside, and the Z values are the kind of X and Y axes here. So we're looking for 0.05, right? 0.05. Did I write 0.5? I did, didn't I? I meant to say 0.05. 0.5 is 50%. 5% is 0.05. Way to go. 0.05, yes. 0.05. 0.5 is 50%. 0.05 is 5%. Don't let me make those mistakes. This is why you're supposed to be in class and speak up and correct me. All righty. Coming back. 0.05. There we go. 0.05. I think it's about right here. Kind of between, wait, no, that's 0.005. Hello. Let's go bigger. Too big. 0.05. Where are, ooh. There it is. It's between those two numbers. So let's see, if I zoom out, we can see what that Z value actually is. It looks like it's negative 1.6 between those two. So negative 1.645, which is exactly what I said it would be. Negative 1.645. And now, again, the upper boundary of that, the positive Z star, should be positive 1.645. Let's check it. Going back, where is 0.95 on this thing? 0.95, 0.95. Remember, if you don't have this table anymore, you need it. If you have lost this table, you need to go on Apex and reprint it, or let me know and I can help you get access to it again. So there's 0.95, and it corresponds to the Z star 1.6. Between those two, 1.645, just like we thought. Okay, so that's where those numbers come from. So I can use this method to find any Z star for any confidence level I want to. So let's talk now about calculators. What if I want to do the same thing using a calculator? So they can do the exact same process we just did with using our standard normal table. Do the exact same thing on a graphing calculator if it loads here. I'll show you. Oh, it's already there. Clear. By doing inverse norm. So remember, if you go second vars to the distributions menu, this third option, inverse norm, it allows you to input the area below a value that you want to find the value of. So I want to find this negative Z star. I would say, okay, well, below negative Z star, we're expecting 0.05, 5%. The mean of our standard normal curve is 0. The standard deviation of our standard normal curve here is 1. And I can hit paste. And it will give me the value that makes that happen, negative 1.64. It's actually more accurate than what we got in the graph, in the table, negative 1.645. And again, we can use that inverse normal function in here to find any percentile of any normal distribution. So it doesn't even have to be the standard normal curve. It can be any area that we want down there, any proportion. We used this a bunch last semester if you don't remember. So now again, I can double check the positive Z star here should have 0.95 below that value. Again, it's standard normal, so I'm gonna leave that at 0 and 1. And there's the positive 1.645, just like we expected. So let's see if we can do the same thing now for a confidence level we have not talked about yet, 85%. So by hand, 85%, so 0.85. What's remaining of the 100% would be, sorry, this bugged me. kind of keep that in the center. What's remaining of the 100% will be 15, right? 100 minus 85 is 15%. So there's 15% within these two tails. Split that in half, we get 7.5%. So as a decimal, that'd be 0.075. 0.075. So I can quickly go into my table and look up where is the area going to be 0.075. 0.075, 0.075, right here, looks really close. That is negative 1.44, negative 1.44 is that Z star, which means a positive Z star should just be the positive version of that, positive 1.44. Okay, let's check it using our graphing calculator. So on my graphing calculator, I'll go to that option, inverse norm, and I'll put in, I want an area of 0.075 in a standard normal curve, so mean 0 and standard deviation 1. And there we go, we get the exact same thing, negative 1.44. And this is actually more accurate because it gives more decimal places, right? And I could check it even further. I could add up this 0.85 and this 0.075 to find out which percentile this Z star would be in, 0.925. And then do the same thing just to double check that we get the right number there as well. I say 0.925, I think that's what I said. So there we go, positive 1.44, just like we expected. Good way to check your work though. I do want to point out one more thing though. If you have a newer calculator, you actually have even more options. Let me open up my camera here and show you the newer calculators that I have here in class. I think some of you guys have this version of a calculator. Let me move this up. Clear. And this one, when I go to that same inverse norm here, it actually gives you more options. Down here, it says left, right, and center. So the left is what we normally do. The left is what the only option the older calculators will give you. It's what we have in the standard normal table. It just gives you, it assumes that you're looking at the area to the left of the value you put in. Right, we'll do the same thing for the upper. So if you wanted the top 10% on the table or on an older calculator, we'd have to put in 90% instead. But in this calculator, I can tell it to give me the right side, so the top 10% instead of the bottom 10%. That also means that I can look at a center. Okay, if we want the 85th percentile like we just did, instead of having to figure out what the tails are, I can just go ahead and say, what is the 85th percentile? Let's see, standard normal curve. Let's center that. Let's center that area though and see what we get. And then it gives it to me as an interval, negative 1.44 and positive 1.44. So if you have these newer calculators, it's even simpler. So I can do that all day long. If I'm looking for a specific Z star, a critical Z value for a certain confidence level, if you have this, use that center option. You don't even have to consider what the tails are in this case. So that's super helpful if you have your calculator. Anyways, so that's it. That's 2.1.